Hey, video number 5 on energy. We're looking at gravitational potential energy, kinetic energy and elastic potential energy. So the previous video we looked at work done and we looked at power, and we also mentioned about this idea about conservation of energy and how it applies to these different concepts. So once again, we're going to be using that idea of conservation of energy towards the end of the video. The 3 specific energy stores that you need to know a little bit about are GPE, kinetic energy and EPE. So I'll make a start with GPE. Gravitational potential energy, obviously. Quick reminder in case you missed this from the first video, if you are asked about gravitational potential energy, you need to say gravitational potential energy. Do not shorten it to gravity. Gravity is a force. If you call it gravitational potential energy and get sick and tired of writing gravitational potential energy, as I'm getting sick and tired of reading that, you can shorten it to GPE. So what is GPE? It's the energy stored in an object due to its position in a gravitational field. What does that mean? It's stored in an object when you hold it in the air. If an object is above the ground, it will have GPE stored in it. The formula is pretty straightforward, although there are 3 things to keep in mind here. The formula triangle works just the same as it would normally. You've got mass times gravity times height. For the higher people, you do need to just be aware that mass times gravity is weight. So to work out gravitational potential energy, you sometimes see it written as weight times height. Now on Earth, there is a number you need to remember, and that's 10 when you're looking at gravitational field strength. When you're looking at acceleration on Earth due to gravity, the special number is 10. Most exam questions would actually tell you that. Kinetic energy is the energy stored in a moving object. Kinetic just means movement. Now you can see straight away this formula is a little bit more complicated. Once again, there are 3 values to keep in mind. 0.5 is a half, so sometimes you see that written out as the fraction 1/2, times the mass of the object times velocity squared. So this is a little bit more complicated simply because of that part there. And there's the formula triangle. Now all I would say is when you're answering questions on kinetic energy, I would certainly consider squaring the velocity before you try to do the sum. So let's give it a quick example. If you've got a car with a mass of 10 and a velocity of 10, calculating the kinetic energy, what I would do is I would square 10 first to give me 100, and then I would plug the rest of the numbers into the calculator. So I go 0.5 times 10 times 100. I wouldn't try and do all that at once. I wouldn't go 0.5 times 10 times 10 squared. There is a reason that some calculators mess that up, and I can't remember what it is, but I would certainly try and do that in stages. Take your 10, your velocity, and square it, and then plug it into the formula. Now, elastic potential energy is the energy stored in a squashed or a stretched object. And again, this formula is very, very similar to the kinetic energy formula. It's a half times k, which is the spring constant, I'll talk about that in a few seconds time, times x squared, and x is the extension. I'm not sure whether that's just a physics joke or what, but x in this case is the extension. And again, square the extension before you plug it into the formula. What is k? What is the spring constant? Well, the spring constant is essentially how stretchy or how squashable a material is. So if you think about elastic bands, you'll have seen elastic bands in your life, you will know that not every elastic band has the same amount of stretchiness. Some are really, really stretchy, others are less so. That k gives us a value that we can use in this formula to tell us how stretchy a material is. So in terms of the foundation people, you can end the video there. This remaining bit is only really for the higher people. And it involves combining these formulas. Now, the example I'm looking at, I'm only going to combine gravitational potential energy and kinetic energy, but you could do the same with elastic potential energy and kinetic energy. It's the same idea. So, it's possible to combine these ideas. For example, if you drop a ball or stretch an elastic band. So a question might ask you to combine those ideas. So we've got this example question here at the bottom. A ball with 0.2 kilograms mass is held 1.5 meters in the air. easy so far, and dropped. Calculate the maximum velocity of the ball as it hits the ground. So my first thought as a student would be to think, which formula should I be using? And a quick look at the two formulas that are going to be relevant. You can see that you've got to use the kinetic energy formula. You're being asked to work out velocity, and this is the only formula that has velocity in it. So looking at the values, we need a half, which is easy, 0.5. We need the mass, which the question tells us. But to work out the velocity, we also need the energy. Now, the question does not tell us how much kinetic energy the ball's got. Luckily for us, we can work kinetic energy out if we know the gravitational energy. How? Well, if we come back to this idea of conservation of energy, so I've got the energy transfer diagram. It's a bit more complicated than it probably needs to be, but it's just starting us off here. Person's got chemical energy stored in their muscle. Through a chemical reaction, that chemical energy is transferred to the ball as gravitational potential energy. They let the ball go, and the force of gravity transfers the gravitational energy into kinetic energy. So as the ball hits the ground, the kinetic energy in the ball will be the same as the energy it started off with. Remember, conservation of energy means the energy at the end has to be the same as the energy at the start. So if the kinetic energy is the energy at the end, gravitational energy is the energy at the start. If we know the energy that it had at the start, we can work out the amount of kinetic energy we have at the end. I've included this bit because the same is true. If we know how much gravitational energy was in the ball to start off with, we also can work out how much chemical energy must have been in the person's muscles to start with. But more on that later. This is the relevant bit. So how do we do it? Well, first of all, to work out the velocity, we need to know the kinetic energy, so we need to work out the gravitational energy. Now, there's two ways of doing this. The simple way, which is actually a little bit more complicated, there's a few extra steps involved, is to first of all work out the gravitational energy and then plug that into your kinetic energy formula. So gravitational potential energy is mass, which is 0.2, times gravity, which we know is 10, times height, which is 1.5. Times those together, it'll give you the gravitational energy, and as I've just said, if we know the gravitational energy, we know the kinetic energy. So then you can plug that energy into this formula, rearrange it to give you V. And remember, if you're working out V, this formula tells you V squared, so you would need to square root it. The answer is 5.48 meters per second. So if you want to have a try at that, you can see if you can come out with 5.48. The other way of doing this, which is more for the mathematically inclined, will be to combine those two formulas. Now, that's a little bit more extra work, but it means that you can do it in one sum, and the answer will still be the same. So once again, that is quite a complicated idea, and I've got under no illusions that I will have probably spoken very quickly there. Having a video means that you can obviously pause the video and return to what bits you aren't really understanding. If you still don't understand it, as is the case with all these videos, please drop me an email and I can try and explain it again.